Thank you very much. I'm so grateful for the opportunity to speak at this conference and to congratulate Maxim on his birthday. So he contributed to many areas, and this is one of them. In fact, our discussions with Jan certain comment on one aspect of Kontsevich-Soibelman theory of wall crossings. So since the background was already briefly recalled yesterday by Jürgen Andersen, I took it, I thought that I'll write the background thing on the board right away and just explain it quickly. So the point is that we translate events and structures in the original plane, sort of analytic functions with divergent behavior, irregular singularities, asymptotic sectors, and so on, into the other plane, so-called Borel plane, by means of some kind of Fourier transform. And this is goes back to the procedure of Borel summation. So in good cases, what happens after we do a version of Fourier transform in the complex domain, we obtain functions which are much they resolve this behavior. We get functions with many singularities, often regular singularities, but functions possibly multivalued. And to analyze such things, so the point of our approach with Jan is that perverse sheaves and their generalizations are a natural tool for analyzing multivalued functions. So we took it upon ourselves as an exercise to see what can we say about, from this point of view, using the language of perverse sheaves. So, of course, in this correspondence, the product of functions becomes additive convolution, and one feature of the singularities in the Borel plane is that they have very often, in good non-trivial examples, they have some additive structure. They, for example, fit into arithmetic progressions, or they fit into a subgroup in the complex plane, and so on. So the idea here that we do some kind of navigating those singularities, trying to avoid them, kind of traveling among them without hitting them, and so on. And that is a language of perverse sheaves is very well suited for that. So here I just wrote an overview of Borel summation. So we start with a series which kind of are interested of its behavior at infinity. We do term-wise Fourier transform, so it's one of the sort of formulas of the classical analysis of distributions. This something like this goes into something like this. So and the front board. Okay, yes. Yeah. This one. Oh, it's fixed. I apologize. Oh, okay, well, okay, better, yes. Yes, so I'm simply saying that we do term-wise Fourier transform, then because of division by factorial, things start converging better. In good cases, it sort of has non-trivial radius of convergence, and in really good cases, it extends to analytic function, probably multivalued, and we do the inverse Fourier transform. And this calls the Borel sum, provided it converges and provided we avoid the singularities. So a standard example is the Euler series, something like this. It goes into geometric series, something like this, but it has singularity w = 1. So if we integrate from 0 to infinity, we have to make a choice. So this, of course, gives the ambiguity in the Borel sum. So, in fact, my talk will be most of my talk will be extremely elementary, and the other part will be speculative. So I'll discuss how we navigate singularities from the point of view of perverse sheaves. And I consider the most elementary theory of this, where everything is finite. So in fact, it's so elementary because I will consider only perverse sheaves in one dimension. So on a Riemann surface, or in fact, eventually would be on the complex plane, you know. Something like this. So I will consider the situation when we have finite number of singularities. That's the elementary theory of perverse sheaves. Yes, in set A. So the elementary theory says that we have the category of perverse sheaves on X with singularities in A. So, such a perverse sheaf F, if it restrict to the complement, is a local system L in degree 1, shifted. So this local system in the classical language accounts for the multivaluedness of the function, but more interesting thing is what happens at the singularities. And the simplest example, again, it's no, it's in degree -1. Yes, it's always confusing. Maybe in the last month I learned how to do it. So kind of it's fixed because it was no, but I think it's like this. Yeah. So the most classical example, X equals disk in C. A is just 1 point, to something like this. So by using of a certain cut here, we have the theorem that perv of disk 0 is the category of data consisting of vanishing cycles and nearby cycles, such that the condition that T psi, which is 1 minus UV, and T phi, which is 1 minus VU, are invertible. Those are known as the monodromies.
Because the invertibility is the same for equivalence.
Yes, there is a mini theorem that one follows from the other.
Now, if it's finite dimensional, yeah.
So from what I remember, there's some formula which kind of universal.
No. If it's infinite dimension, if spaces are infinite dimension, it's not the same.
Okay. So anyway, let me say it like this, and I consider the most classical, most elementary setting. So this is space of nearby cycles. It is something like, it's a stock of this F minus 1 at a point epsilon. It's a stock, and this is the space of vanishing cycles. So since we have those are invertible, we get local systems with those monodromies, which I write thick phi and thick psi are local systems on S1. So this is this super elementary part, and from there we can understand how to navigate singularities if there is more than one of them. Let me call this part transport mapped. So suppose we have 2 points in A, B, and A. And suppose we take a path which joins a point A with a point B, path gamma, which avoids other points, C, 0. So gamma. Then what we can do, we can take a disk around A, we can take a disk around B, apply this situation. So apply the example above. And then we have the diagram. We have phi corresponding to A. So more precisely, it's the stalk of that local system at this particular tangent direction, right? Then it goes to psi at A, which is the stalk here, would be UA. Then by monodromy, it goes to psi B, and then by VB, it goes to phi B. So we have a map, sort of M, so M, AB of gamma, phi A to phi B. More precisely, phi A is the stalk of this local system here, and phi B is the stalk of that local system here. So it's an invariant under isotopy. Isotopy means when we move the path, but we don't hit any other singular points. But we can ask what happens if we hit other singular points. And the corresponding statement is a version of the Picard-Lefschetz formula. In fact, it can be sort of considered the simplest wall crossing. So it says what happens when we move it across a singularity. Suppose we have a point A, we have a point B, we have a point C. Suppose I have a path gamma from A to C, and we move it across B. It would be path gamma prime here. So then when we do this, then in the process, there are two other paths here. Let's call them alpha and beta. And the formula is that MAC of gamma prime, the result, the crossing this wall, equals MAC of gamma minus MBC of alpha, MAB of beta. So it's, on one hand, it is just an elementary exercise on the definition of phi and psi and t phi.
Here you should be a bit careful because you point B to arrive in two directions.
Yes. There is, yes. There's some identification, yes. Yes, so. Yes. One has to fix it, yes, exactly. So now one can ask, so first of all, it walks and talks like a Picard-Lefschetz formula because this is quadratic modification. But a relation to the usual Picard-Lefschetz is obtained as follows. We can apply this to what we call the Lefschetz perverse sheaf. So suppose, again, in this classical setting, we have a potential, superpotential or an action. So it's a dimension n+1. So proper holomorphic. With isolated singularities. So then we have the set B is set of critical points. It maps to the set A critical values. And we can form the perverse sheaf as follows. We first take the direct image under W of the constant sheaf K sub X. K is some field of characteristic 0, but this is a complex, and we can let's take it zero-dimensional perverse homology. What? K, Y, you're absolutely right. Yes. So it's a complex, and perverse T structure kind of slices this into perverse homology. and consider LW is this, and let's call this the Lefschetz perverse sheaf. So its properties are that the space of vanishing cycle at the critical value A is space of classical vanishing cycles.
So you have to normalize the dimension properly.
Yes, yes, yes. I'm talking about it. Yes, at x0 always.
No, but K, the constant sheaf is not perverse.
Yes, yes, yes. You're absolutely right. It should be, again. Now I know this. It should be n+1. Yeah. Now, yeah. Yes, 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 yes. Yes. So for W, yeah. So, for example, in the classical sense, for a Morse critical point, it would be generated by the classical vanishing cycle or corresponding cohomological cycle. So B, delta B equals K times delta B if Morse. So this vanishing cycle will be here. Yeah. And the phi, the psi, maybe I'll use this part of the board. So psi at some point equals middle cohomology, middle of W minus 1 of some epsilon. So that's the Stokes of this local system. So from this we see that this data of vanishing cycles and transports is more somehow more algebraic than the much more complicated structure, which is the cohomology of the fiber. So what I want to say that Picard-Lefschetz formula, so this formula for LW is the usual Picard-Lefschetz. How do we see it from the definitions?
From the W, yeah.
What do you mean from? So first of all, we get a perverse. It is connected because if we apply this formula for this particular perverse sheaf, we get what we classically understood by Picard-Lefschetz formula for a function with. In fact, there are many many ways of saying what is a Picard-Lefschetz formula. So here I want to consider the most universal formulation where there is no geometry, only perverse sheaves. This, of course, is a testament to the importance of this concept, which this concept has built into itself the non-trivial properties of geometry.
Is it possible to write down the perverse definition of what the vanishing cycles are? Because I mean, typically it's the joule of the space of micro solutions, but what's the perverse?
Okay. So where this? Yes. You can say it's sort of well, the key word here is again Fourier transform. So we say micro solutions, or we have Fourier transform. So let me put it like this. It is so we have this disk. It would be R gamma. Suppose this K is R gamma maybe of this hyperplane H at F. It will be in one direction, or R gamma is suppose a K in F, when K is just this. So from an analytic point of view, this is sort of. No, suppose we study the Fourier transform, then we need to look. Suppose we study Fourier transform in the complex domain. So I write something like this. That first of all, this needs to converge, right? So it has to be somehow to live in the area. The cycle should be such that the integral of the cycle converges. It should be such that the exponential decays on the endpoints of the cycle, which goes to infinity. So the cycle should go like this. So and this sort of accounts for this this formal language of vanishing cycles, it kind of matches the analytic thought of Fourier transform. Now, let me sort of focus on the idea that, that this thing is more fundamental. Let me call this part localized perverse sheaves. So we consider the quotient category, perv of xa bar, which is perv of xa, modulo the local system, modulo those which don't have singularities, perv x empty, which is simply local systems on x, so by -1. So if we do this, if we ignore this, then we will ignore this data, but this data will remain. So phi a, MAB of gamma, descend. So OK for f bar in perv bar, but psi does not. So this was first considered by Gelfand, McPherson, Valonen. It's 96. So, and I want to get a slightly more natural formulation of the result, and the result I recall later.
What does it mean to take a quotient of two categories?
It means that, so naively we say that the objects of this are said to be zero. Naively, but more to the point, we say that the category had the same objects, but morphisms, space of morphism from A to B in the quotient category is a certain quotient of the space of morphism in the original category.
Not quotient, it's you have to go zigzag.
No, it's, I mean, Serre quotient. So it's like it's a Serre subcategory. Like we consider kind of like an original paper of Serre on classes of abelian groups. We consider abelian groups modulo finite abelian groups. So yeah, so anyway, this is a natural construction. What I want to say is the following proposition. So this data, they determine the category. So perv bar of xa is the category of data which consider first of local systems phi a log S1a, data m AB of gamma from phi a to phi b, subject to Picard-Lefschetz data. Somehow this makes it's more natural that the category is invariant under the diffeomorphism or homeomorphisms of this surface, the topological invariance. So this as an aside, so this allows definition of perv or bar when A is infinite by discrete. Infinite. So if we consider already this situation, then if we want to go back to this picture, then we will have to consider local system and perverse sheaves with infinite dimensional Stokes. But the interesting case is when everything is finite dimensional here. So this is the kind of essential skeleton. So now may I probably erase this part.
Just a second.
Yeah.
Did you consider this situation when as this set moves and points collide and you got kind of like
parameters, please?
No, we don't consider it now. It's very interesting, yes. And I remember your talk in China, you were saying something about this. We are not, yes, we are not doing this. Yeah. Maybe we should, but so far.
Resurgence is parameters.
Yes. So far we didn't do it, yeah. So now let me consider something more specific corresponding to x equals CW. So in the complex plane, so there are two issues. First, when we do Fourier transforms and stuff, it's not a topological procedure. It's a structure which has to do with linear additive structure on the complex plane. And there is also this additive structure which I want to discuss. And this is the theory of Gelfand-McPherson-Vallone. So I recall how it proceeds. This is CW. We take a point, V, somewhere far away, and we form a spider, like very common in singularity theory, which means join every point of A by a path. B was gamma B, and call this spider. Set of non-self-intersecting point, A to V. And we consider the transports, particular transports, corresponding to the path which goes from A to V and from V back to B. So in fact, this picture is also maybe more familiar if we do it like this. So, and somehow they converge to point V at infinity. We consider MAB with respect to spider K, so this is spider K. It is MAB of A to V to B. To B, A to V to B. Yeah, so this we call it the Vladivostok transport. Yes, it's almost the same. Yeah, so this may be Khabarovsk, and this is Vladivostok. Yeah. So we draw everything very, very far away, and then turn it back. So this is the approach, as you know, that how we mathematicians think.
Dangerous. You can cross the Chinese border.
Yes. My lips are sealed. Yes. Okay. Okay. So. Yes. So and the result is that pair of x of CA is using K. So to the category M sub n, which consists of phi A with data is invertible TA, and MAB from phi A to phi B, which can be arbitrary. So n is the cardinality of A. So in this case, from that point of view, what is being said here is this type of paths, they form a system of representative of all the other paths, modulo Picard-Lefschetz conditions. If you want some other path, then we kind of move them through, each time acquiring the discrepancy.
So you give it for every pair or adjacent pairs, or? No,
for all of them.
All pairs?
All pairs, not adjacent, it's like a matrix.
No, but MAB for A not equal to
Here, MAB not equal to B, or you can put MAA here, sort of say, yes, not equal to B, absolutely, yes.
And there is no relation between MAB and MB?
Yes, no relations, yes. So it's sort of the representatives. The idea is representative paths modulo Picard-Lefschetz. But of course, again, anyone who is not a mathematician would think that it's very unnatural to do such transport. And if you want to go from point A to point B, the most natural thing would be to go along a straight line. Let me call it rectilinear transport. I call it M of the interval AB. Well, simply take from point A to point B, but for this to work, we need to assume that there are no points on exactly this interval. So we say AB intersected with A equals empty. So this open interval, there is nothing. So and then a version of this would be a proposition. If the set is such that this holds for every pair, so that it's a linearly general position, if then the M of AB and the same TA, so define another identification. Of perv bar of CA to MN. So it's another set of representatives. Oh, okay, I'm doing 4. So the reason of why this is more natural is that they are useful for Fourier transform.
So what does it land on MN?
MN is the category of such data.
And n is a number of elements.
And N is the number of elements.
I understand, but now you have MAB for every pair AB. So are there relations between them that...
No, it's the same. So I see there's a category such that consisting of those data. So, and the way it is defined here, those MAB using the spider. Yes, and here it's just direct.
Maybe we can say it's also break group acts.
Yes. Another way of saying this traditionally, like in singularity theory, that the topological invariance of the concept of perverse sheaves is reflected in the fact that the braid group acts on the set of isotopic classes of spiders, which in fact is a principal homogeneous space.
Can you choose any family of passes that are like simple passes that don't intersect the set in the interior? Or this?
I'm not sure about this statement. Probably something like this is possible. I'll sort of mention another approach, sort of the end, when we still want to have straight lines, but if there are some points on the intervals. So that's an interesting question, but we'll get there in a moment. MAB is useful for Fourier transform. And that's natural because in Fourier transform we'll look for like the areas where the exponential decays, and the decay area of exponential is some half plane. It's actually a straight half plane with a straight line on the boundary, so the line geometry becomes important. So Fourier transform goes like this. Suppose we start with a perverse sheaf. We lift it by the Riemann-Hilbert correspondence with a solution functor to a holonomic regular D-module C of W dW, holonomic regular. For this, just this formal Fourier transform, which replaces W and dW, called M check, is a C Z del Z mod. So it will be holonomic, but typically not regular. And from this, by forming solutions, if you want, we get a new perverse sheaf, perv of C. And it is sort of this procedure is well known. It goes back to Malgrange and then Katsarkov, Kontsevich, and Pantsev. In this particular case, they made it more precise. that the new new model has only one singularity, has only one singularity at z equals 0, and it is regular and irregular at infinity. So this means that the new perverse sheaf is very topologically, it's very trivial. It belongs to category perv of CZ0. And one can understand, it was described, the precise structure. So in this new plane, with Z plane, there will be only one singularity at 0, and phi 0 of this check equals psi, so general stock of F, and psi, so general stock of F. So this will be a local system outside 0. It will be the total space of vanishing cycles of F equals direct sum over A and A, phi A of F. So if you want to look at this local system, then this, again, becomes kind of irrelevant. It is relevant only at the singular behavior here. That is not the most interesting part. The most interesting part is here. And as I said there, so it descends. So this descends. This thing descends to a pair of hat and carries a Stokes structure. So in fact, it's using this. So the question is how to determine this Stokes data, and this. And the natural language for this is this type of transport. This is in our paper with Soibelman and Sukhanov. Is that the Stokes? So now when I say Stokes matrix, there are again several meanings to this. There are local Stokes matrices, how things sort of change by elementary wall crossing, and there's a global Stokes matrix which classifies this Stokes structure. And I mean here the global Stokes matrix via M of AB is the decategorification, if you want, verification of the so-called algebra of infrared of automorphisms. So in that theory, there is certain complex, which is sort of direct sum over some convex paths, convex piecewise linear paths. And here, in this Stokes matrix would be alternating sum over such paths, plus minus compositions of these transports. So one can say, so this problem of calculation, the Stokes matrix, is the simplest version of this. So I won't go there more precisely. Oh, there is one more. Okay. But from sort of general point of view, it's of course unnatural to try to find the Stokes data or the Fourier transform in terms of such transports. It's much more natural to do it in terms of linear transports.
So you say that you can describe the Stokes data, that which is now using your description of perverse sheaves?
Yes, using in terms of those transports.
The rectilinear ones,
Rectilinear ones, yes.
which are more natural for.
They are more natural, yes.
But it's just a restatement of chapter 12 of Malgrange's book.
Of course.
It's proved by Malgrange.
Yeah, his book on linear.
The green book.
The Birkhauser one.
Of course, yes, of course. But what's interesting is this sort of parallelism. And just one more statement here is by Katsarkin, Kontsevich, Pantev, is that the quotient category perv of CA is identified with a subcategory called perv 0 of CA, set of F in perv of CA. For this, all the cohomology of CF equals 0. So it's basically orthogonal of the constant, orthogonal to constants.
Now you're working with finite dimensional Stokes or more general?
What? No, so far I'm talking just about finite dimensional Stokes, and then I will say something that we can theoretically apply this to more general situation. Yes. So all I'm saying is very elementary. Now let me discuss, as a part 4, the concept of alien derivatives in this situation. Let me call it alien derivatives for perverse sheaves. So now suppose A is not necessarily in general, not necessarily in linearly general position. Then we can start from a point A and go to a point B, but there will be a few points in between, A1, A2, some kind of AR, some number of points in between. Then what we can do, we can go and avoid, we can do transport with avoidances. For example, like this. Again, this is sort of a natural construction for perverse sheaves, and we can encode them by sort of plus or minus. Suppose going to the left is minus, goes to the right is plus. This is going to be minus. We can have something called MAB epsilon 1 epsilon r from phi A to phi B, which means avoid or AI on left if epsilon I equals minus, on the right if plus. So for example, if I write MAB plus is the same as MAB plus plus. We can do all the way. So, and the formulas for alien derivatives, they sort of lift naturally to this context. And let me call this the alien transport. Called MAB delta. So this is the same formula as in Resurgence, or epsilon 1, epsilon r, number of pluses of epsilon, factorial, number of minus of epsilon, factorial over r plus 1, factorial, MAB epsilon. So it can be written also in several other forms. For example, for example, for r equals 0, we just have AB, m AB delta equals m of AB. For r equals 1, A1, m AB delta would be 1/2 m AB plus m AB minus. So, and so on. In general, we'll have the following feature that have positive coefficients. All they sum to 1. And this thing is stable under introducing dummy singularities, which means that if we assume that there are many possible singularities here, but in fact there is no singularity, then no matter how we compute it, the answer will be the same. So stable under. So this concept is sort of naturally belongs to the theory of perverse sheaves. Okay, so let me maybe do it here. So and another version of this proposition that a localized perverse sheaf, if we associate this phi A with TA and MAB delta, is also an equivalence, like this. And the ln derivative proper is a certain combination of those. It would be, suppose omega is a complex number, so I recall that phi of f equals direct sum phi a of f. So delta omega equals delta omega. No, there's no check here. Yeah, omega is from phi a, phi of f to phi of f. So it has matrix elements corresponding to this decomposition. Delta omega a to b equals 0 if b not equal to a plus omega, and a b delta if b equals a plus omega. Then not so much. Okay, I wanted to get to more speculative part, but let me just say a little bit about the additive convolution. On perv 0. So, and this goes back to the work of Katz, middle convolution, and more recent book of Resurgence on exponential motives, which is more systematic, slightly different treatment. So if you have the addition from C cross C to C, so here we have F and G, F and perv CA, G and perv CB, perv 0 of CB. Then we define their additive convolution, simply R of plus star of the cross of the external product. So, and the statement, this from Resurgence, that A F star G and perv 0 of C A plus B. So it's actually, again, a perverse sheaf. And B, sort of a Thom-Sebastiani formula that phi at a point C of F tensor F star G equals direct sum over A plus B equals C, phi A of F tensor phi B of G. So it's a can be called Thom-Sebastiani formula. It means that phi tot, so total phi of F tensor G star G equals total phi of F tensor total phi of G. So and we want to add to this the statement that alien derivative, so it's a kind of tensor functor. So we want to add this, that alien derivatives are alien transports are derivations of this tensor functor. In which delta omega is a derivation of phi. It means that delta omega corresponding to F star G, it would be act on this, and it is equal to delta omega F tensor 1 plus 1 tensor delta omega G. Again, this can be also seen from the point of view of Fourier transform as this logarithm of elementary Stokes matrix in direction, as sort of was pointed out, was described by Malgrange.
So to have this equivalence of category using this averaged thing, alien transport, but if you instead just choose some sides for every pass, do you still get an equivalence of categories?
What do you mean two sides?
So instead of this thing with the epsilon, suppose you choose.
No, but there's probably a version, but we haven't thought about this. Yes, yes. Somehow those seem to be the more fundamental. Okay, so now in the remaining few minutes, let me say what I actually wanted to say. Let me maybe do it here. Part 6. Now I want to say that we should consider algebras with respect to convolutions. So our proposal, so in Resurgence, study a sort of generalized perverse sheaves, not necessarily such elementary perverse sheaves, but certain generalized perverse sheaves. Which are algebras with respect to convolution. Or so commutative, or maybe not commutative, non-commutative. Maybe also modules over algebras, some algebraic structures. Because under convolution, the set of singularities is added. So if you have an algebra, then typically we will not have a finite set of singularities. So that's why we need to sort of understand generalized things. So one thing that we should consider, I think, is the only localized perverse sheaves. And it is good when A is discrete, but there is also another direction when A is non-discrete. And maybe I don't have time to speak about this. It's not so easy. So let me just consider a couple of examples which are natural in this possible examples which are natural in this context. So first of all, there is a trivial example of an algebra. We take an object, we take a perverse sheaf, and let's take its symmetric products in that category. We'll get an algebra, a graded algebra. Each graded component is still of finitistic nature. And the version of this would be like this. One example would be lifting the cohomological whole algebra. Lifting. Because cohomological whole algebra is constructed out of vanishing cohomology. So vanishing cohomology is the global, is the phi total of something. So we can look at the something of which it is phi total. So and then we'll very likely get an object of this nature. Suppose I have a QW, query with potential. Then we have, for every dimension vector, we have representation D of Q with corresponding trace of potential double Q. And then coha D is H dot of rep D, and then we have phi WD of K of some sheaf. Yeah, and this is an associative algebra. And so this is, we can write phi total of some perverse sheaf or a graded perverse sheaf FD in per C, when this is simply the Lefschetz perverse sheaf LWD of K. And those FD, for the same reasons, form an associative algebra. So direct sum FD is a convolution algebra. This is interesting because we add to the structure of Koha, we add the transport data for this perverse sheaf. We look at what are the critical values and how they are connected in the C plane using the transports. And another example, I also wanted to say it, but maybe I'll be very brief.
Sorry, what was phi total? Still the sum of the...
Yes. So this thing has several critical values a priori, right? So in some cases, the only critical value is 0, so we don't get anything new. But in some cases, there are many other things, and they have their life. And so again, this Koha concept can be applied to other things when you have potentials, like Chern-Simons, holomorphic Chern-Simons, and that becomes interesting. So each time there is a convolution algebra hiding there. Borel is called the cluster perverse sheaf. Perverse sheaf. So it is goes to work of Kontsevich Soibelman. And Gayot-Mornitsky. Which are saying that cluster transformations as Stokes matrices. That's quite interesting that we have coordinate changes as Stokes matrices, which means that the matrices live in the space of functions. So there is what is also hiding here is a kind of generalized or localized perverse sheaf. CW. So maybe what time is it? It's already time to stop. I'll just say that So if we have gamma is a symplectic lattice, for example, is of rank 2, symplectic lattice with a central charge function to C, then A, we take to A is Z of gamma. So in principle, there can be higher rank. In this case, it will be non-discrete. So it would be, but in this case, it would be a lattice. Something like this. And if we can extract, so extract Stokes matrices from the transformations, we get, so log of these transformations, I call it what? K gamma, log K gamma, they give by the alien derivatives, give M A B delta, and from there we get a localized perverse sheaf. Although with infinitely many singularities, so in general, so to finish, these algebraic structures of all kind, I think, are important to reflect the additive structure on the singularities in the Borel plane. So the singularities, they usually arrange in some arithmetic progressions or arrange into a lattice or arrange into something. And this seems to be a reflection of algebraic structure, which it would be interesting to look at. So I'll finish here. Thank you very much. Thank you.
Questions?
This business like cluster transformations as Stokes, do you actually mean Stokes matrices or like Stokes automorphisms?
Stokes automorphisms, yes, yes.
It's a non-linear pop.
Yeah, no. So how should I say? So we have the group ring C of gamma. Yes, we have group ring C of gamma. We want to view this as a total space of vanishing cycles of some perverse sheaf. Perverse sheaf which would have individual spaces of vanishing cycles of dimension 1 and some connections between them, some transports given by this data. And if you look at how those transformations are given, they have exactly the same shape as in the Malgrange description of the Stokes data. They only go in one particular, the matrix elements are situated in this exactly this particular direction.
I mean, is it possible to view this in a simple example as like a restatement of Borel's sort of change of?
I don't know if it's exactly the same as Fourier, but it's sort of very similar anyway.
The other question I had, this logarithm of elements. So the Stokes matrices are supposed to be sort of generators of the differential Galois group.
Yes.
And so the alien derivatives are thus,
they correspond to the Lie algebra of the differential.
Galois derivation.
Yes. Of course. Yeah.
So in this example with the lattice and the homomorphism to C, I suppose you want the image to be discrete. What are the MAB gamma? I mean,
what I'm saying, so so there are some particular cluster transformations written here. If you look at their matrix elements, so from the matrix elements, so they sort of live in the completed direct sum of this. And the matrix elements sort of are the same as it will start from A, only go to A plus gamma, maybe then A plus 2 gamma. So the matrix elements would always be like this, which is exactly the same shape.
You did something to know what the...
Yes, we need to know the name. Yes, I skipped this, yes.
Other questions? No. Let's thank Mikhail again.